Okay, so the point of today's lecture is to give you a sense of what we can do within the confines of integer programming. So we've had a couple of examples, throughout the semester where I've talked about how you can convert these constraints into a linear equation without too much trouble. We've talked about constraints such as each airplane can only be traveling between 2 cities at a given time, or one movie can't be shown on multiple screens at the same time. So there's lots of ways to phrase these things linearly. But there are some other things we want where it's not so clear how to do it linearly. And there are 2 places nonlinearity can enter. They can enter as the constraints, or where else could they enter? So what else do we have? We have the constraints and we have the function we want to maximize, right? Maybe the function we want to maximize is not a linear function, right? So the question is, how do we handle these nonlinearities? And so what I'm going to do today is I'm going to describe a bunch of techniques. The details are already written up nicely in the notes I've posted on how you can convert a bunch of statements that do not seem initially to be within the confines of integer programming or linear programming into integer programming or linear programming. So what I want you to see is that these things are a lot more versatile than you might be led to believe. So can someone give me an example of a continuous function? This is the who's awake right now. Continuous function. X squared. Of course, this isn't a linear function, right? So can anyone give me an example of a continuous linear function?
X.
There we go. Can anybody give me an example of a continuous linear differentiable function? Still X, yes. Right? It's still a good function. Now consider the following. G of x is the absolute value of x. Good function or bad function? Bad, right? In the confines of integer programming or linear integer programming or linear programming, this is a bad function. In terms of life in general, what do you think? Good function or bad function?
Still bad.
Still bad. Why is this bad?
Not differentiable.
Not differentiable. Right? Not differentiable. It is a horrible function for that reason. This is why in statistics we measure error by squaring and not with absolute values, because now all the techniques of calculus are applicable. And so for those of you who took probability with me, you'll remember, hopefully, we professors feel that if we say things like you remember, then you actually do remember. You'll remember, hopefully you remember, you might have seen in passing, the method of least squares. Where if we measure error by squaring, then by calculus and linear algebra we can get to the exact answer, for the best fit parameters. If we use absolute values, it's a nightmare. So here's the question. What if I had absolute values in my linear programming problem? Is this good or bad? So what do you think? Could I use this? Is this a linear function?
Yes. It's linear.
It's not linear.
But if it's above
G of 2 plus 3, for instance, is not G of 2. I'm sorry, G of 2 plus the negative 3 is not G of 2 plus G of negative 3. If we only had positive inputs or we only had negative inputs, then yes, it would be linear. But if we allow ourselves to the general case, and so for instance, even though the variables we care about might only be non-negative, it's possible that combinations of them might actually have negativity. So for example, we might want to consider some kind of profit. And so maybe you have a deal with the movie theaters, and you get so much money for the first so many tickets, and then for each additional ticket, maybe you get a different amount. So we might have things like maximum and minimum coming into play. And so maybe, maximum and minimum enter. So for example, maybe we have a term that's like maximum of x in 100 times 4. This could be one of the terms in our profit. Or maybe we could have something like this. Maybe it's 3 times the minimum of 100 of x. So maybe no matter what, we have to pay the owner, we have to pay George Lucas $100 or 3 times $100 if we want to show his movie on 3 screens. And then maybe X is the number of people that want to see it. If it gets above a certain level, then maybe we have to start paying George Lucas additional amounts. But we could easily have constraints like this. I am not carefully preparing this lecture, as you can tell, as to exactly what, that doesn't matter. The idea is that minimums and maximums will occur. That you can have these cutoffs. And it makes sense, you have a certain guaranteed amount of money you have to pay out, but then if certain things happen, then you're liable for more. And this is a way, in some sense, to kind of minimize your risk. You don't commit to too much up front. And so you might often have, contracts in the financial industry structured like this. We have a certain guaranteed minimum amount that you'll be given, and then if things reach a certain level. When I was selling a house years ago, I actually wanted to set the contract up like this. Because when you're selling a house, let's say you're selling a house for $400,000, and the realtor gets a certain percent. I'm just making up numbers. Gets 10%.
What was 10%? Is it?
They get 10% of how much the house sells for.
Who would get?
The realtor, the person
Oh, okay.
who's selling the house for you. So if the house sells for $400,000, they get $40,000. If it sells for $500,000, they get $50,000. Let's look at these values. Is there much of a difference in how much the realtor gets? No. The realtor maybe can sell the house very quickly at $380,000. Or spend a lot of work and maybe eventually find somebody for $420,000. What's the best use of the realtor's time? Since this is being recorded, I will leave it like that. But a contract like this, where you get a certain percentage, is not necessarily advantageous to all parties. Because the extra $20,000 or $40,000, that's huge for you, as the seller of the house. But for the realtor who's only getting 10% of that extra $20,000 or $40,000, the house is not going to sell below a certain amount, it's not going to sell above a certain amount. It's that, sweet middle in between. How much work should the realtor do? And something like this indicates that, it may not be in the realtor's best interest to try to get the absolute highest for you for a long time. Now, of course, there are reasons why you may want to sell the house quickly. But what I'm hoping you can see is that you're going to want to be able to put in minima and maxima into these constraints. That when you're trying to find these objective functions, minima and maxima are quite likely to occur. Other things that you might want to see is or, and maybe and. Right? If some condition, then A, else B. And this should seem similar to the minimum and maximum, right? If we don't have a certain amount of people who want to see the movie, then we only pay you this much money. But if more than that number of people come in, then we owe you this much. And that contracts could be structured like this. And of course, instead of doing an if, you might have, if you've done programming, you might have a switch. You might have if condition 1 this, else condition 2 this, else condition 3 this. And of course, if you have multiple conditions, you can just do it through nested if statements. Okay, so I go through a bunch of other things, in the notes. So the question is, how can we handle constraints like this within the confines of linear programming? So there's a lot of reason to want to include stuff like this. But again, if we want to include these things as written, our functions become nonlinear. And so how can we incorporate these in a linear way? So if you've never heard the expression before, Turnstafel. Have you ever heard of Turnstafel? There ain't no such thing as a free lunch. You don't get anything for free. There is a trade-off. We can take stuff like this and we can linearize them, but there's a cost. So what is the cost going to be? What do you think the cost will be to linearize things?
More constraints.
More constraints and what else?
Variables.
And more variables. So it's going to be a trade-off. So for us, we can linearize by adding constraints and variables. Is this a good thing to do? Well, I mean, we have a system to solve linear programming problems. And so if we can convert these to a linear programming problem, we can then throw the machinery at it. And so in that case, it is worthwhile. Now the problem, of course, is that this increases the complexity of what we're studying. And it may increase it to such a level that we can no longer solve it in a reasonable amount of time. But of course, you know, we have a method that solves linear programming problems. We want to put everything into this form. It may be better to try to develop a theory of nonlinear programming. That this may not be the most intelligent way to group the algebra. And so this is a big thing. Just because you can do something one way, yay, the theorist is happy, but that doesn't mean from the applied point of view that this is how you should go. You have to evaluate the trade-offs. And so a lot of times, there are algorithms we have that will calculate things, but they calculate things so slowly, it's not worth doing. You have to find a better way. So maybe when we convert this to a linear programming problem, it becomes impractical to solve. But at least there's a chance by doing this that we can solve it using methods we know. Another one of my favorite quotes is about the singing horse. You know, what's amazing is not that the horse sings at all. It's not that the horse sings well, but that the horse sings at all. Right? And just the fact that you can take something like this and make it linear and then apply these methods, that's still a wonderful fact. So what I'm going to do is I'm going to show you how to convert some of these things. And so I think the first one to do is the OR statement, or the... it's a binary indicator variable. Oh, that's the first one. Binary indicator variables. So if you take probability or some other courses, you might see binary indicator variables all the time. They're 1 if something happens and 0 if it doesn't happen. So it's a very easy way to see what's going on. And so for a lot of problems, it's nice to be able to just have this quick way to tell, did the condition happen? And so we're going to make a couple of assumptions. And so just so I keep the notation the same, okay, so we're going to assume 1. Every expression is at most, I'm using that. Right? There's some number, everything I'm looking at is at most n. Is this a reasonable assumption? Let's look at the profits for Facebook. What can you tell me about how much Facebook will make in the next 5 years?
Unpredictable.
Can you give me some information about Facebook's profits?
100 billion.
Is that an upper bound or a lower bound? Let's be safe. You know, Googleplex dollars, right? Facebook will make less than $1 Googleplex dollars in the next 5 years. We're all reasonably confident making something like that. So for a lot of these things in mathematics, we don't necessarily need, you know, an optimal value. We just need, is there some upper bound? Now in terms of runtime, it might actually be better to have a reasonable upper bound. You know, and not feel like, you know, Dr. Evil. But yes, you know, there will be some number. And then the next, we're going to have a discreteness. So I think I want to use delta for that. everything is a multiple of some delta. So is this a reasonable assumption that everything we measure is a multiple of some discrete unit delta? Well, let's think back to Facebook. You know, if you look at how much money it's making, we can consider everything in multiples of cents. If you want to think of stocks, you know, going to be integral multiples, right? If you want to think of how many pages it's going to create, you know, it does make sense that we can have a discrete thing. We only have finitely many things we're going to consider. Each one of them will have some discrete unit, and then we just take basically the product of all these, you know, different decompositions. We take something so small that it goes evenly into all the different possibilities. Right? So if the smallest thing for one thing is, you know, 1/5, another is 1/3, another is 1/10, we can take our unit to be 1/30. And everything would then be a multiple of 1/30. So it's not an unreasonable assumption to assume that everything is a multiple of some fixed unit. And again, no one is going to be solving linear programming problems by hand, right? We're going to use a computer. So if you use a computer, what are you working with? What does a computer work in? Binary, zeros and ones. The computer is fundamentally forced to be discrete. This is not a restrictive assumption. Right? Everything we're going to be looking at, this is a very reasonable assumption. Alright, so now I'm going to give you 3 conditions to encode. So what we want to do is we want z of a to be 1 if a is greater than or equal to 0 and 0 otherwise. So this is going to be a nice way to encode is a positive. Okay, and here are the 3 conditions. So the first is ZA is in the set 0, 1. The second is A divided by N plus delta divided by 2N is thus equal to ZA. And then, does the camera still get this over here?
Yeah.
Okay. And then the last is ZA is less than or equal to 1 plus A over N. Okay. And this does the job. Okay. So let's see what goes on. So the first is ZA has to be either in 0 or 1. Is there a mistake, Rhoda?
Oh, it's ZN under.
It's 2 times N. This is why all my Z's have a line through them. So Z is either in 0 or 1. Okay. So let's look at this expression. ZA has to be greater than or equal to this expression. Okay? Now, we want, let's say A is 0. If A is 0, delta is positive, what does that force ZA to be?
0. Should be 1.
Forces it to be 1. So, if A equals 0, 2 implies ZA is 1. If A is greater than 0, this is also going to force ZA to be 1. Right? Because remember, this is positive and that will be positive, so this has to be. So if A is greater than or equal to 0, then the second condition forces ZA to be 1. Okay? What if A is negative? What's the largest negative value Z? What's the largest negative value A could be?
Negative. Almost.
Negative what?
That thing.
Negative that thing, negative delta.
Yeah.
Right? So the largest negative value of A is negative delta. If I put a negative delta here, plus delta over 2n, what would I get?
Minus delta over 2.
Negative delta over 2. And what does that tell us about ZA?
Can be either 0 or 1.
Either 0 or 1. So if A is less than 0, true implies nothing. Okay? So condition 2 forces ZA to be 1 if A is non-negative, and gives us no information otherwise. What do you think condition 3 is going to do? Without even looking at it, just seeing what condition 2 did, what do you think condition 3 will do?
With the last condition. Wait.
I'm sorry?
So we would do with the last condition, like nothing shows up, and then the third condition we do with that.
So what is condition 3 going to do?
A is less than 0.
But it's going to handle now, it's going to make ZA 0 if A is less than 0, and then do nothing, I think, if A is greater than 0. So now, if A is greater than or equal to 0, let's see what 3 does. Well, if A is greater than or equal to 0, this number is greater than 1, or greater than or equal to 1, so there's no information in ZA. So it does nothing. And if now A is negative, if A is less than 0, then 3 forces ZA to be 0. Right? And so what's nice is each of these conditions handles half the case that you need and is harmless the other half of the time. And this now allows us to introduce binary integer variables. And of course, is there anything special about having A greater than or equal to 0? What if you wanted A to be greater than or equal to 100? What would you do?
A minus 100.
Yeah, A minus 100, right? There's nothing special about 0. We just look at A minus 100. So we can have these threshold values. And we can get them very easily. So what we can do is we can say, if ticket sales are below a certain amount, well, we have now a test for this. And so, for instance, these 3 simple conditions, we'll try to keep them up on the board as long as possible. So maybe when we're trying to find out our revenue, we have to pay George Lucas $100 no matter what. And if we have more than 200 people, we have to pay, say, $4 for every person. And so then it gets a little harder how we maybe figure this out. Or maybe we could have things in different ranges. Maybe we have to pay him an extra $50 for the next 100 people above 100. And then $25 for the next 100 after that. So maybe we then owe him another $50 if we have at least 100 people. And then if we have at least 200 people, we first pay the $50 for having more than 100, and then we pay maybe another $25 for having over 200. And then maybe we pay another $12 for having over 300, and maybe we pay $6 for having over 400, and at this point George Lucas is satiated and says that's fine. And so again, you could of course have finer breaks than this. And I'm not saying that this is the best way to do this, but I'm saying here is a nice way to have a step function of how much money you have to pay. If you have fewer than 100 people, you only pay George Lucas $100. If you have between 100 and 200 people, you pay $150. If you have between 200 and 300 people, you pay $175. And so on and so on and so on. Now, of course, the problem with this model is you go from paying $100 with 99 people to paying $150 for just that one extra person, and then there's no additional charge for the next 99 people. Okay, this is of course not the optimal method to do. But if you have enough stratified levels, then this is not a bad idea. And then yeah, you'll have a few places where there are these jumps, but if you put in enough of these variables, you've essentially approximated a continuous function. The other thing is to just try to come up with, as a nice exercise, a way to write a better linear function that takes into account how many people you have. But the idea is not to give you, the full, complete, 3-semester-long course in linear programming. It's to give you an idea of how you can make this stuff work within the confines of what we know. So any questions on what we've done so far on how to introduce binary indicator variables and how we can now apply them to having revenue issues like this, of having things switch on and off. Okay, I'm going to break it here.